Okay, so let's get started now. Welcome back, everyone, to MATA02, the magic of numbers. Today, we're going to be continuing on with modular arithmetic, and we're going to be focused on division today. So remember, we talked all about addition, subtraction, multiplication, and powers, and they all sort of made sense, right? So you do one way of doing them is to do them in ordinary arithmetic, and then divide and take the remainder, and that gets you the answer. But somehow, remember, that's basically asking, well, you do the normal operation and then you divide. But now, how do you do division then? Like, what is that? Do you do, like, if the normal modular operations require division, and what does modular division do? And it turns out that this will be quite different, and this is very complicated, which is why we have sort of built up to this and not done, and it wasn't on the midterm for that reason. Okay, so let's go back to how we invented division in the first place. So we invented it, right? So this is just reversing multiplication. And let's say we haven't invented fractions yet. Because back when we were starting with the integers, we hadn't yet invented all these other fancy numbers like fractions and rational numbers and all that. But now, the basic definition, right, was if z times y is equal to x, and x divided by y is equal to z. So the original purpose of division was just to reverse multiplication. So let's give a quick example of that. Hopefully you guys all know how to divide by now. But so as a quick example, I think this is the one I usually use. So this 3 times 5 is equal to 15. So 15 divided by 5 is equal to 3. Or we can also write it in ratio form. So 15 divided by 5 is equal to 3. So even though we haven't invented fractions, you still can use the sort of fractional notation for division if you want to. It still makes sense so long as it's well defined, right? So this is ratio notation. So basically what we mean by that is 15 is to 5 as 3 is to 1. That's the same relationship between them, right? Okay. So let's remind ourselves again. So this should be a relatively easy question. When does x divided by y make sense as an integer? So this is one of the things we covered early on. Like, when does it make sense? Does it always make sense? Or does it only make sense under certain conditions? And remember, we haven't invented any fractions yet, so you only have whole numbers. And one thing you have to be careful about is, well, can you divide by 0? So does it always make sense, or does it always make sense, but only, or does it make sense only so long as y is not equal to 0? Or does it only make sense so long as x is a multiple of y, or if both b and c are true? Q. Wait, Q. Is that an A? Oh, yeah. Okay, but anyway, it looks like people are voting B. So that is partially true, but remember, because things like 5 divided by 0 is undefined, right? But remember, we don't have fractions yet. So 5 divided by 2 is also undefined. So undefined because we only have integers. So the answer is actually D here, so long as both B and C are true. Remember, we're going back to the land before we had invented all these fancy numbers. So all we've invented is counting numbers. In fact, we haven't even invented negative numbers yet. All we've invented is 0, 1, 2, 3, 4, counting up through infinity. And so in this case, you need both B and C to be true. Because if 5 divided by 2, if it's not an even multiple, we haven't defined what that means. And we remember we did 2 different ways of doing it. One way that we tried to solve this was by inventing these fractions. Another way that we tried to solve it was by taking remainders. And those are both things we can do, but this doesn't make sense as integers if it's not an actual multiple. You have to do something different. Okay, so now that we've done set that up, let's talk a little bit about division in modular arithmetic. So we know how to multiply in modular arithmetic. Here's the multiplication table. You can also do this by just computing it, which you guys all have tons of experience with now. But you can also reverse things, right? So 4 times 3 is equivalent to 2 mod 5. And that's something you can see because you can just look here. 4 times 3 is equivalent to 2 mod 5, right? And this is sort of like saying 4 times 3 is equal to 12. Well, if we had 4 times 3 is equal to 12, then we'd also have that 12 divided by 3 is equal to 4. And so we can fill in the slots in the same way. So that is to say, 2 divided by 3 is equivalent to 4. Okay, because remember, we don't know anything about fractions. So if you're trying to think of it in terms of fractions, ignore all that. We're starting from first principles. We haven't invented what fractions might mean in modular arithmetic if we're ever going to. So all we have is, but we do know that division is the opposite of multiplication. It reverses it. And so you can use these same patterns and define, well, 2 divided by 3 is equivalent to 4 in mod 5 arithmetic. Does that make sense? You're just reversing your previous operations. Ignore everything you know about fractions. That'll just confuse you. So, well, what is 2 divided by 4? So remember, you're reversing operations. So 2 divided by 4, what would that be? Okay, so it looks like people are guessing D. That's equivalent to 3. That is indeed correct. Because of course, 4 times 3 is equivalent to 2. And so 2 divided by 4 is equivalent to 3. Okay, great. So it seems like everyone's got the hang of that. So what about, let's assume, and I'm just going to, I already know this because, well, we knew 2 times 4 is equal to 3 mod 5. So what is 3 divided by 4 mod 5? Okay, yeah, that's exactly right. We're just reversing things, right? So this is equivalent to 2 because you're just reversing things. So if you had 4 divided by 3, that gives you 2. So one way of looking at it is if you have a multiplication table, when you're doing division, you can just look to see what row or column, let's say you're starting with this. Actually, I think I normally do this with columns. So let's say, let me circle this other one, actually. 4 divided by, see, 2 times, no, well, that's fine. 2 times 4 is equal to 3. And so you can look this, in order to get 3 divided by 4, you look to see the row or column with the 4, and then look to see where 3 appears. Okay. What is 3 halves, or 3 divided by 2 mod 5? Okay, so it looks like we have a little bit of disagreement here. Well, again, if 3 divided by 4 is equivalent to 2, then 3 divided by 2 has to be equivalent to 4, right? And why is this? Because what we're doing is whenever you're doing this division, you first look to see where the 3 that comes from a 2 times something, and you look to see what else it multiplies by. So when you're doing 3 divided by 2, that's equal to 4, and when you're doing 3 divided by 4, that's equal to 2. Sorry, I'm going to use the word equal a lot when I really mean equivalent in modular arithmetic, so hopefully that's not too confusing. Okay, so that seems a little bit more complicated. Does anyone? Yes. So the basic premise here is that we have 2 times 4 is equal to 3, right? So that means if 3 divided by 2, that's equal to 4, because it's the other thing that you'd have to multiply it by in order to get 3. And 3 divided by 4 is then equivalent to 2. So it's sort of like when you have, let's say, 2 times 4 is equal to 8, right? If 2 times 4 is equal to 8, then that means 8 divided by 2 is equal to 4, and 8 divided by 4 is equal to 2. And so we're just doing the same thing, except multiplication is weird, and so therefore division is weird. Excitement, confusion. Okay, so some excitement. Okay, Good. Still lost. Okay, don't worry. We'll be doing a lot of these. So let's do the next one. Yeah. Or I guess like I'll try to explain one other way, which is if you have a multiplication table, that allows you to do division, right? So if you have a multiplication table, the way you do division is you look to see where a number appears in that multiplication table, and then you look to see what the two things that multiply together get it for. And if you divide by one of those two things, you get the other one. So let me throw you all a curveball. What is 4 divided by 3 mod 5? So in order, note that I didn't tell you in advance this time what times what is equal to 4. Oh, okay. So let's see, what are people guessing? People are guessing 2. Out of curiosity, why do people think it's 2? Why is 4 divided by 3 equal to 2? You can put that in chat. Since I'm trying to understand, but that happens to be incorrect, and I'm trying to understand what's going on. Go on. Oh, sorry, what was your answer? Oh, interesting. Okay, so I think we're getting confused about multiplication versus division tables. So I think what's happening is 4 divided by 3, you're taking 4 and 3, and you're like, oh, well, that gives you 2, right? That's not correct, because that's saying that 4 times 3 is equal to 2. So that's saying 4 times 3 is equivalent to 2. But that's not what we're trying to reverse. So what that would tell you is like 2 divided by 3 is equivalent to 4, and 2 divided by 4 is equivalent to 3. Yeah, that's a multiplication table. Sorry, it's not a division table. Okay, so given that, let's have you all try again on that one. So that's a multiplication table, and so you have to reverse it in order to get division. Let's see, I think I have another color. Yeah, I have orange. Okay, and in order to reverse it, basically what you're asking is there a number such that when you multiply it by 3, you get 4? And the answer is yes, there is. Because 3 times 3 is equal to 4. So we have 3 times 3 is equivalent to 4, and therefore 4 divided by 3 is equivalent to 3. Or in other words, 3 squared is equivalent to 4. As an aside, this also means that 3 is the, that 4, that 3 squared is equal to 4, and you can also think of some other weird things that happen as a result of that. But we're not going to worry about that yet. Weird stuff happens with powers and roots as well. Okay, so given that, let's go to mod 7. So this was mod 5. Let's go to mod 7. I don't actually mean mod 5 and mod 7, I just mean mod 7. And this is again a multiplication table, so you'd have to reverse it in order to get the division. So find 4 divided by 3 mod 7. So again, the whole point is, and let me write this out. You need some value x such that x times 3 is equivalent to 4. Okay, and it looks like some large fraction of people are guessing D. Well, let's take a look. So we need some value that times 3. So if you're multiplying times 3, what you can do is you can be like, well, I can just look at everything in the 3 column. That's everything times 3, right? And then I look down and look to see if at any point it's equal to 4. And it is indeed equal to 4 at 6. So what that means is that 3 times 6 is equal to 4, or 6 times 3 is equivalent to 4. And therefore, we know that 4 divided by 3 is equivalent to 6. Okay, because all we're doing is we're reversing multiplication. It's just harder now because you can't use the ordinary multiplication and division tables that you know from grade school. You have to use these weird multiplication tables and understand that you're reversing it. Okay, let's do another one. What's 3 divided by 4 mod 7? Okay, it looks like people are guessing 6 again. Well, let's see if this is correct. So what do we need? We need x such that 4 times x is equivalent to 3, right? Because you want 4 times something that's equal to 3. And so if we're looking in the 4th column here, what is it equal to times that? What does it multiply by to get you 3? Well, it's down here in the 6th row again. So 4 times 6 is equivalent to 3. And so 3 divided by 4 is equivalent to 6 again. Oh. And let's try one more in the divide by 7s. What's 3 divided by 5? Okay, it looks like you guys are starting to get the hang of this. So what do we need? No, you will not be given the multiplication tables on the test. I'm using these multiplication tables to illustrate what's going on. Remember, you can construct all these multiplication tables, right? You can just multiply them and take mods. Also, we're going to learn another technique for solving these that doesn't require staring at multiplication tables. I'm just using these to illustrate the basic principle before we go on to more advanced techniques. And it turns out that we'll be connecting together various ideas from different parts of class. For example, maybe the Euclidean algorithm could be helpful somehow. I'll just throw it out there, but we'll get to that later. So what we need is we need x times 5 is equivalent to the 3. And so what times 5? We're looking in this column. Well, and there. So 2 times 5 is equivalent to 3. And therefore, 3 divided by 5 is equivalent to 2. And one thing to note is that you don't need the entire multiplication table, right? You only need the column that corresponds to a particular value. And so even if you weren't given the multiplication tables in advance, you could be like, oh, well, I'm going to be in the 5 column. 5 times 0 is, that's 5 times 0, 5 times 1, 5 times 2, 5 times 3, 5 times 4, 5 times 5, 5 times 6, right? That's 0, 5. This is 10, but that's equivalent to 3. And then this is 15, so that's equivalent to 1. This is 20, and that's equivalent to 6. This is 25, and that's equivalent to 4. And this is 30, so that's equivalent to 2. Okay? Remember, because you know how to do multiplication, so you can construct this table pretty easily. Okay, so all that's great. But now let's talk about some other ways of doing multiplication. Or sorry, doing division. So we have this way, which is you have to stare at this big table, find the right column, and then find where it matches, right? But when you're doing ordinary multiplication, well, there are other ways of doing ordinary multiplication. Or sorry, ordinary division. So when you're thinking back to ordinary numbers, is there another way of doing it if you have fractions? Simplify, yes, that helps. Simplifying is actually a little bit dangerous for modular arithmetic, which we'll get to a little bit later. Cross multiplication, okay. So another way of doing it, though, is you can use reciprocals, right? So if you're in the regime of ordinary numbers, say 3 divided by 2, one way of doing that, so we're going to go back to ordinary decimals now. One way of doing that is that's equal to 3 times 1/2, which is equal to 3 times 0.5, which is equal to 1.5. Okay? So one way is if you know the reciprocal of a number, you can just multiply, right? So now the question is, do we have reciprocals of numbers in modular arithmetic? So now in the ordinary integers, without fractions, you don't have any integer. You don't have any reciprocals except for the reciprocal of 1, right? Or the reciprocal of -1 if you have negative numbers. All the other numbers are fractions. But now it turns out that a weird thing happens in modular arithmetic, which is you often have reciprocals even without having fractions. So for example, 2 times 3, that's equivalent to 1 mod 5, right? So you have two numbers that multiply together to give 1 in mod 5. But what does that mean? That means that, so you can also say 2 is equivalent to 1 divided by 3. And 3 is equivalent to 1 divided by 2. Because remember, if you have two numbers that multiply together to give 1, then you can think of that as the reciprocal of it. Let me give another example, which is a little bit weirder, but it'll make sense in a little bit. So 4 times 4 is equivalent to 1, right? So what does that mean? So that means that 4 is equivalent to 1 divided by 4. This probably looks weird. Can anyone give me an intuitive explanation for why this is true? And I'll give you a hint. When you're working with ordinary integers, well, yes, because you're multiplying 4 by itself. When you're working with ordinary integers, when is a number its own reciprocal? So let's suppose that we're working with ordinary integers. When is x times x equal to 1? When is that the case? Or put it another way, when is x squared equal to 1? When x is 1. Oh, and also, I think there's a, is there another case when x is equal to, x squared is equal to 1? Remember, you're allowed to use negative numbers as well. So yeah, -1. So x is equal to plus or minus 1, right? So if you have negative numbers. But now, this should make sense now, because notice 4 is equivalent to -1 in mod 5, right? So 4 is equivalent to 1 in mod 5, and so therefore, 4 squared is equal to 1, because -1 squared is equal to 1. Okay, I'm getting a few looks of confusion, but we'll carry on for now. And we'll just say that when a reciprocal exists, you can use it for multiplication. What do I mean by that? So for example, if I wanted to do 4 divided by 3 mod 5, one way we could do it is we could go look at the multiplication table 2 slides back, and then look to find the right column and find the right entry. Another way to do it is you can say that this is equivalent to 4 times 1 over 3 mod 5. And so that's equivalent to 4 times 2, because 1 over 3 is equivalent to 2 from over here, mod 5. That's equivalent to 8, which is equivalent to 3 mod 5. Okay? So if you know the reciprocal of a number, then it just becomes a matter of multiplication. And multiplication is easy, right? Multiplication, you just throw the numbers in, and then you divide and find the remainder. Okay, there's still some amount of confusion in the chat, but okay, let's keep on going. You should ask me questions as we go along, because this is one of the most difficult concepts that we'll be dealing with in this class. Square roots and cube roots will also be the same sort of difficulty, because we're doing the reversing of things. But I'm going to ask you all, will you be using division with larger numbers? Yes, you will. Don't worry, we'll get there, but not yet. You're starting with the small numbers because you can just sort of match things with small numbers. With big numbers, we will be talking about the algorithms that you use. So it turns out that you can use things like the Euclidean algorithm to figure these things out quickly without having to just match a bunch of things, which is a part of the connections that we're trying to make in this class. Like techniques you create in one area, even though they're in a different number system, you can still use them in this other number system. So I'm going to ask you, what's 2 times 3 divided by 5 mod 7? Did I zero this out? I don't think I did. Let me zero it out. So now there's, of course, a question, right? Like, what do you do first? Do you do the division first? Do you do the multiplication first? Doesn't matter what you do first. Okay, so it looks like we have a lot of people who've answered C, which is 4. And well, let's try to figure this out. So let's do it a couple different ways and see what happens. So one way is this is equivalent to 2 divided by 5 times 3, right? Well, what's 2 divided by 5? Well, that means you're looking for something times 5 that is equal to 2. So that's 6, right? Because 6 times 5 is equal to 2. So that's equivalent to 6 times 3, which is equivalent to 18, which is equivalent to 4. Okay, but you can also do it a different way. So for example, we could also try doing it 2 times 3 divided by 5. Well, what times 5 is equal to 3? Well, that's over here, that's 2, right? So that's equivalent to 2 times 2, which is equivalent to 4. So you get the same answer. We can even do it a different way. So this is also equivalent to 1/5 times 2 times 3, right? And so that's what divided by 5, what times 5 is equal to 1? Well, it's 3, right? So this is equivalent to 3 times 2 times 3, which is equivalent to 18, which is equivalent to 4. Okay, so however you do it, so you have 3 different ways of doing it. They all give you the same answer. And this is quite important. This won't always be the case, but it is the case under certain conditions, which we'll talk about in a moment. And when this is true, when division is well defined, you can do it in whatever order you want. This is sort of like how we gave you several different ways of computing modular powers, right? You can use these equivalences and then put them in, and then that should give you the same answer. And if they don't give you the same answer, something went wrong. And so this is another way for you to check your work, because I should also mention that there are a couple different ways of checking your work, right? One of them is you can just multiply everything back. Another way is you can try to solve it in several different ways. And you should get used to also solving in multiple different ways so that you can check when things have gone wrong, right or wrong. So the punchline here is that multiplication and division are associative, and so you can do them in any order so long as the reciprocal is well defined. What do we mean by that? Well, let's take a look. So we've done 5 and 7. What is true about 5 and 7? So what kinds of numbers are they? What kinds of numbers are 5 and 7? Yes, exactly. They are both prime numbers. So what happens if you do this with a non-prime number? Let's say 6. 6 is a very not prime number. It's one of the least prime numbers you can get in small numbers. There's a well-defined sense in which you can say that, but let's just say that it is a very not prime number. So let's say we're doing division mod 6. Well, I just wrote out the multiplication table mod 6. So what is 2 divided by 5 mod 6? Oh, did I zero out? I don't remember if I zeroed that out. Let me zero it out, so please reply if you did already. Okay, so people are saying it's 4. Okay, well, let's take a look at that. So we have the same procedure. So what we need is 5 times x is equivalent to 2. Well, 5 times what? 5 times something is equivalent to 2. So we have 5 times 4 is equivalent, oh, sorry, that's the 5 times 4 is equivalent to 2. And so therefore, we know that 2 divided by 5 is equivalent to 4. Okay, so that all seems to work all right, right? Let's try another one. What about 5 divided by 0? So I'm going to remind you all that weird stuff happens when you divide by 0 in the integers. So you should actually go through the procedure. What is 5 divided by 0? Okay, so let's work this through together, since I think people just took the shortcut of saying, oh, well, anything took a shortcut there. So what do we need? We need x times 0 is equivalent to 5, right? Because you're dividing by 0. So you need x times 0 is equivalent to 5. For what x is that true? Well, let's take a look at the 0 column here. So we have the 0 column. Which of these numbers times 0 is equal to 5? And notice, well, 0 times 0 is equal to 0, 1 times 0 is equal to 0, 2 times 0 is equal to 0, 3 times 0 is equal to 0, 4 times 0 is equal to 0, and 5 times 0 is also equal to 0. So this doesn't work, right? There is no such number. So there's no such number. And so you can't divide by 0, which shouldn't come as too big of a surprise because you can't divide by 0 normally either. Okay, so that's all well and good. You normally can't divide by 0. Well, let's try a different one. Let's throw that out. What about 2 divided by 3? So you don't have to worry about division by 0, but what is that equal to? What number times 3 is equal to 2? Okay, yeah, so you have the same thing happens here in a slightly different way. So what you need is you need x times 3 is equivalent to 2. So if you're in the 3 column here, well, is that equal to 2? No. Is that equal to 2? No, 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 no. So again, there's no such number. So this is again E, no such number. Okay, so you'll notice division seems to have gone haywire when we're working with the number 6. Okay, and I'm going to ask you one more, and think really hard about this one before you answer. I'm telling you right now, there's a trick to it. What is 4 divided by 2? Yes, there are 2 answers. So division goes super wrong when you're dividing by 4 divided by 2 because you end up with 2 answers. So let's see that. So what are these 2 answers? Well, what you need is you need x times 2 is equivalent to 4. Well, that seems easy. One answer is x is equal to 2. 2 times 2 is equivalent to 4. But we also get a second answer. X is equal to 5. 5 times 2 is equivalent to 10 is equivalent to 4. So that's because in this column, you have 2 different places where you can get 4 out of it. And so you don't get a unique answer. And so this is actually not uniquely defined. Okay, so you might be wondering, okay, fine, like that particular one is not uniquely defined, but maybe it's still useful to be able to like say something along the lines of 4 divided by 2 is either equal to 2 or 5. But you end up with additional problems when you do that. So there are some problems with non-uniqueness. So I'm going to go up to mod 12, and I'm just going to make these claims. 3 times 2 is equivalent to 6 mod 12. 9 times 2 is equivalent to 6 mod 12. And 3 times 6 is equivalent to 6 mod 12. Okay, and you should be able to check these because this is, well, 3 times 2 is equal to 6. 9 times 2 is equivalent to 18, which is equivalent to 6. And 3 times 6 is also equivalent to 18, which is equivalent to 6. Okay, but then what if I ask you, what's 6 divided by 3 times 6 divided by 2? I'll give you a moment to think about that. I probably should have put a poll on here. But so when you get an answer, tell me in the chat. Can you cross multiply? That's a very good question. What is cross multiplication? So note the name of the slide is problems with non-uniqueness. So, okay, so we have one answer. So someone's guessing 6. Does everyone get 6? Or can you get something different? Yeah, you can also get 0. I'm not sure if you can get 2. You might be able to get 2. I didn't get, like, that's not one of the ones I got, but it's quite possible I didn't get all of them. But so notice, this is equivalent to, well, we know that 6 divided by 3 is equivalent to 2, and 6 divided by 2 is equivalent to 3. So one way of doing this is 2 times 3, which is equivalent to 6. Okay, great. But another way of doing it is you notice that this is also equivalent to, if you just multiply everything through, this is 36 divided by 6 mod 12. But 36 doesn't exist as a number, right? So 36 mod 12 is just 0, right? Because 36 is a multiple of 12. That's 0 divided by 6 mod 12, which is equivalent to 0. And you can solve it a couple different ways. Another way is you notice that this is also equivalent to, because, oh, sorry, I don't want to use that color. Let's use red. So note that 6 divided by 2 is also equivalent to 9. And 6 divided by 3 is also equivalent to 6. And so this is also equivalent to 6 times 9 mod 12, which is equivalent to, wait, did I do that right? 3 times 6. Oh, yeah, well, I think that's right. So that's 54 mod 12, which is equivalent to 6. So now we have a question. Hopefully I did that right. But regardless, there are ways of getting multiple answers because of this non-uniqueness. Because you don't have uniqueness to begin with, you can get all sorts of different answers depending on what choices you make. So if you submit one answer, can we get full marks, or do we have to find all answers? So this is where it becomes really important to know exactly what I'm asking. So the way it will normally work is if I ask this sort of question, the answer will be there are multiple answers and it's not well-defined. And if I just ask you this question, you need to figure out that this is not a well-defined operation, because I have some operation and I get multiple answers out of it. There will be some cases where I might ask you to find, because there are so many answers, how do you know which one is right? Well, either all of them or none of them. For the previous slide, if you get an answer where there is no numerical answer, do we put the answer as not uniquely defined? So there are basically 2 aspects to this, right? So sometimes when you divide, you just don't get an answer. So there's no answer. Sometimes when you divide, you can get multiple answers, in which case there isn't a unique answer. There are just multiple answers that all sort of work, but that doesn't make for a well-defined operation. Because when you divide by something, you want it to be a number, right? And when you get 2 numbers out of it, then it's no longer a number. So if I ask you what is, if I ask you what's 4 divided by 2, sorry, if I ask you what 4 divided by 2 is, then the answer, then there is no answer because there are multiple numbers that satisfy that, so it's not a well-defined operation. On the other hand, if I ask you what number times 2 is equal to 4, then there are 2 answers. Okay, but this is one of the problems that happens, right? Because normally you don't have this problem where division gives you multiple answers. And all of a sudden, when we're working with modular division, you get this weird stuff happening. So the question is, when does this make sense? Oh, yeah. So does this mean that modular division doesn't fit with other math properties because there are exceptions and not one solid answer? That is a very good insight. It can, depending on, so it doesn't quite fit in. And so you have to do more work to try to make it fit in. So remember, when we had division previously, one of the things you did is you could invent new numbers. You can invent new types of things to make things work. But now the question is, when does this make sense as a modular integer? Modular integer. So remember, of course, it's just the opposite. So when does this make sense? And let me actually add as a unique mod. a unique modular integer. So you get multiple answers, things also go wrong. So when do you not get multiple answers, and when do you get exactly one answer for division? Is basically what we're asking. Okay. So notice that each column of the multiplication table gives all multiples of that number, right? And so the question is, when are those multiples all possible numbers? So notice the multiples of 0 are 0, so you can't divide by 0. Actually, I should mention, the answer here is none of the above. You need both conditions B and C, but there is an additional condition that in order for division to be well defined, and we'll talk about that in a moment. So notice that you can't divide by 0 because that you don't get all possible numbers. If you try dividing by 1, that works. If you try dividing by 2, maybe you can divide some numbers by 2, but we notice that every single number that appears in that column appears twice. And so you don't get any unique answers. The same thing happens with 3. The numbers here appear 3 times. And more interestingly, it also happens with 4. So you also can't divide by 4 because you don't get a unique answer. But you can divide by 5. Actually, let me do this in slightly different colors. So things don't go wrong when you divide by 0. Things go wrong when you divide by 2, when you divide by 3, and when you divide by 4. But you can divide by 1 and by 5. Okay, so now this should be a little bit confusing now. Hopefully it's a little bit confusing. And what should we do? What should we do? So, is it fine that do we not need all divisions to make sense? Or should we invent more numbers? Is all of math pointless, and this is all just a game let mathematicians play with themselves? Or it's fine, the number doesn't have to be an answer. Okay, so it looks like many people are on the side of inventing more numbers. So that was the strategy that we mostly used back when we were working with ordinary integers. It turns out that for modular arithmetic, for reasons that will become apparent on the next slide, that's not usually what we do. Instead, what we usually do is we actually normally do A. And there'll be a reason for this, which is that for many common numbers, nearly all divisions do make sense. And the question is, what are those numbers? So I'm going to rephrase this question slightly. In mod n arithmetic, when are the multiples of an integer t all of the integers? Oh, sorry, not all the positive. No, all of the integers. Yeah. When are they all the integers? And please answer in chat. So I want you guys to think back to Wednesday now. When they're all in multiples of an integer t, which I've written because it might correspond to something we did last Wednesday, when they're all the multiples, all the integers. Okay, so someone's getting closer when it's not a divisor. So t has to be more than just an integer, and when it's not a divisor, it like gets you some of them. Ah, yes, when t is relatively prime to the mod. Yep. So remember, we did this whole exercise. So I put you out in circles, I gave you weird plus things, you tossed them around. That was basically looking at all multiples of the tossing number. So from that, you can figure out that it's true that this is precisely when n and t are relatively prime. The other reason I had you guys do the exercise on Wednesday is because notice that this is one slide in this lecture. One of the reasons math is so hard is because things that take an hour's worth of playing games to figure out, you can in a math class is just thrown in as a single slide, and then you have to learn it and memorize that. And this is one of the reasons why math is so hard, is just that you're having to learn all these things that took people hours and hours and hours to figure out in 5 minutes. Okay, and that is, so notice that in arithmetic mod n, that means we can divide by any number t that's relatively prime to n, right? So let's not use string. In mod 6 arithmetic, that's a 6 arithmetic, can only divide uniquely by 1 and 5. Okay? But there are some special numbers. And basically, the prime numbers are special because when you're working with the prime numbers, every number except for 0 is relatively prime, right? That's the whole point of being a prime number, is that every other number is relatively prime. And so you can divide by any number except for 0. So in mod 7, arithmetic can divide by any number except 0. Yeah, so 0 is still special. So you still can't divide by 0. That hasn't changed. But basically, the reason why we don't have to invent new numbers is because if you just restrict yourself to working with prime modulus, then you can still always do division. Now, if you're going to work with a non-prime modulus, then things can go wrong. But for this reason, it turns out that a lot of number theorists strongly prefer working with prime numbers. And this is one of the really cool facts about prime numbers. So like earlier, we just talked about how prime numbers, oh yeah, they're a number that's only divisible by 1 in itself. And you can use them to like build up other numbers. But turns out there's much deeper connections of prime numbers to these various kinds of arithmetic. So somehow things just work when you're working with prime numbers in the way that they don't when you're working with most other numbers. And I think with that, I will go ahead and end this class. Note, I will not have office hours today since I will be marking your your midterms. Look for the quiz and your assignment and the ungraded problems on the website. They're all posted there. And I will see you all on Wednesday. So bye, everyone.